Hey everybody, Mr. Judson here. Alright, so today we want to talk about something called trig substitution. And so we have to develop some formulas for this. Trig substitution is used on problems that look like they could be an arcsine or arcsecant or arctangent, but something slightly off. Okay? So, if, these are our rules, if we see the square root of a squared minus u squared, so a is just some number, u is some expression with x's in it, then we want to let u equal a sine theta. And so, when you think about this, if this was in a denominator, it kind of looks like an arcsine. And so that's why we're choosing the sine function. But notice we're sticking a different variable in there. Okay? Again, a is just some number. And so when that happens, if I put a sine theta in place of u, then what I get is the square root of a squared minus square this, you'd get a squared sine squared theta. And if you factor an a out of each of those, an a squared, and you're left with 1 minus sine squared theta, and you want to take the square root of that, well, the square root of a squared is just a, and this right here looks like a Pythagorean identity. This is actually equal to a cosine squared of theta. And so the square root of a cosine squared of theta is just a cosine. So this would equal a cosine theta. So by substituting this into here, whatever expression we have, it becomes this right here. All right. Second formula. If we're trying to solve an integral and we see the square root of u squared minus a squared. Now again, it doesn't have to be in the denominator, it can be anywhere in the problem. This looks like it would belong to an arcsecant. And so what we want to do is we want to let u equal a secant theta. We still got to talk about what happens with a theta, and we'll get there with that. We're just trying to figure out how something like this can become something easier to integrate. All right, so again, if I substitute that a secant theta in place of the a right here, what I get is the square root, I'm going to substitute it in over here. I get a squared secant squared theta minus a squared. So again, I'll factor an a squared out of there. What I'm left with is a secant squared theta minus 1, square root of that, which, again, with the Pythagorean identity, this becomes a tangent squared theta, just like this became a cosine squared theta. And so now I'm taking the square root of a squared tangent squared, and so this whole thing equals just a tangent theta. And that's an easier thing to integrate than this right here is. All right, one more formula. So if I see the square root of a squared plus u squared. Well, with arctangent, we didn't have a square root in there, but we did have something squared plus something squared. So this kind of follows along with the arctangent. So if I have that, then let u equal a tangent theta. And so again, if I substitute that into here, this becomes the square root of a squared plus a squared tangent squared theta. And if I factor out an a squared, then I'm left with 1 plus tangent squared theta. And using our Pythagorean identities, this becomes a secant squared of theta. So the square root of this, that becomes just a secant theta. So again, our goal with trig substitution is to try and take something that we're not really sure how to integrate and turn that into something slightly easier. Okay? Just kind of a heads up on the Central Washington test. When they say solve using trig substitution, we have to solve using this. Even if there's an easier way, we have to show that we understand that rule. Okay? Sometimes there are problems where you might be able to do it a different way, but they're saying no, you have to use trig substitution. All right, let's take a look at an example. All right, so when I look at this, two thoughts would pop in my head. Oh, this is an arc secant because I got something on the outside. But then I'd look at this and go, oh no, wait a minute, those have to be switched around to be an arc secant. Oh, it must be an arc sine. Well, no, because arc sine doesn't have anything out here. So we don't have a way to solve this integral. We have to use trig substitution. So what I see is, I see the square root of a squared minus u squared. And so when we see that, we want to let u, which in this case is just x, so I want to let x equal a, which is 5, sine theta. Okay, so in our rules that we wrote down, you can go back and look at them if you need to. It said let u equal, but u is what's being squared right here. So this is 5 squared minus x squared. So whatever our u variable is, it's going to equal a sine theta. All right? So if I substitute that in here, that means I now have the integral of 1 over, I got to square this, so 25 sine squared theta. And then if I put a 5 sine squared theta in place of this and square it, what I'm going to get is the square root of 25 minus 25 sine squared theta. And remember, in our rule, we said this whole thing, once I factor out the 25, the square root of 25 is 5, and then 1 minus sine squared theta, that's the same as a cosine squared theta, and the square root of that would be a cosine. So this whole thing is going to become 5 cosine theta. All right, we'll get to that here in just a minute. So remember I said we're converting everything over to thetas, and we're going to have to be careful of that? So what I need to do is I need to figure out what dx is equal to. So if I just take the derivative of this implicitly, so dx is going to equal constant. Derivative of a sine is a cosine theta, times the derivative of the angle, which is 1, and I just took the derivative of theta. So I need to take all of this stuff and put it in place of that right there. So now I've got 5 cosine theta d theta. And supposedly we just made an easier problem, right? It's not quite looking like it yet, but let's go a step farther. So I've got the integral. I'm just going to go ahead and put this 5 cosine theta in the numerator. Divided by 25 sine squared theta. Remember, this right here was going to become 25 times 1 minus sine squared theta. That'll become a cosine squared. And so when I take the square root of that, I get 5 cosine theta. So 5 cosine theta d theta. And so now I can cancel a few things, which is kind of nice. So I can cancel the 5s, I can cancel the cosines, and I'll move this 25 to the outside. So what I have is 1/25 times the integral of, I'm left with a 1 up here, so 1 over sine squared theta. That would be a cosecant squared theta d theta. And so now I'm kind of at the point where I feel like, yes, I did make an easier integral to solve because this is one of our formulas. We know the answer to this. And so my answer is, to this integral would be a negative cotangent of theta over 25 plus c. And I'd like to say that we're done, but I started with x's, not thetas. So I now have to convert this answer back to something that has to do with x's. And so to do that, I have to go back to this original piece right here and say, if I move that 5 over and divide, then a sine of theta is equal to x over 5. And so now what I need to do is I need to draw a triangle. This is almost like going back to trig from pre-calc. If I know the sine of theta is equal to x over 5, well then what's the cotangent of theta equal to? So I'm going to draw a triangle here. I'm just going to put it in the first quadrant. I really don't know what the value of x is. Since I don't know, I'll keep it easy. Call this theta. We know sine is opposite over hypotenuse. And so now I've got to find this missing side, which when I use the Pythagorean theorem, I get this squared minus this squared. Which, just kind of as a hint, what you should get here is the same as what you had in the beginning. Okay? If I got something different, I'd probably want to take a closer look at that. So now I go look at this and I think, okay, a cotangent is the reciprocal of a tangent. Tangent is opposite over adjacent, so I want adjacent over opposite. So a cotangent theta is equal to the square root of 25 minus x squared over x. And so that now needs to go back in place of this right here. So my answer becomes a negative square root 25 minus x squared over x divided by 25, which I'll just call that 25 over 1, plus c. And so if I flip this fraction over and multiply, I just end up with 25x in the denominator. So a negative square root of 25 minus x squared over 25x plus c. There's our answer. So let's double check that on our calculator. Speaking of calculator, so this is really important. Those of you who are taking the Central Washington final, we're not allowed to use our TI-89s on that. And so what I'm going to do is I'm going to set up a turn-in checkout time coming up soon, where you will bring in your TI-89, you'll check it in, and I will check out to you a one of those yellow TI-84s. You cannot do the final unless you do that, okay? Real important that we get that. You cannot take the Central Washington final unless you turn in your TI-89 and check out a TI-84, okay? Even if you have your own TI-84 at home, you have to turn in your TI-89. Okay? Alright, so let's check this real quick. I can't remember if this calculator can do trig substitution or not, but we'll give it a shot. So I'll clear off everything I have. I want the integral of 1 divided by, and I got to put this whole thing in parentheses. So I've got x squared times, I'm going to put a multiplication sign in there just to be safe, times the square root of 25 minus x squared. Got a parenthesis to close the square root. I got another parenthesis to close the denominator, and then comma with respect to x, and a parenthesis to end the integral. And so what I got for an answer was a negative square root 25 minus x squared over 25x. So yeah, this calculator can do trig substitution. Amazing. Alright, let's try another one. Alright, you guys go ahead and try this one. Doesn't look like, almost looks like you could do a substitution. Derivative of this is 2x, but because that x is in the denominator, that kind of messes that up. So trig substitution would be the only way to solve this one. Alright, so I always look at the square root and I think something squared minus a number, that usually would go with an arcsecant if I was doing inverse trig functions. So that's the substitution I want to do. I want to let my u value, which is x, equal a secant theta. My a value is whatever's being squared here, so that would be 2 secant theta. And I might as well go ahead and do this. dx equals 2, derivative of secant is a secant theta times a tangent theta. Times the derivative of the angle, which is 1, and I just took the derivative of theta. Really important we keep track of everything that's supposed to be there. Okay, that d theta is important to us. Alright, so this integral is going to become the square root of, I want to put this in for x and square it, so I'll have 4 secant squared theta minus 4 over x is equal to 2 secant theta, and dx is equal to 2 secant theta tangent theta and then d theta. So usually what happens is these integrals get messy but then kind of clean up nice. Okay, I mean we can see right away that I'm going to be able to cancel these 2's, cancel the secants of theta. If I factor out a 4, I get the integral of the square root of 4 times secant theta minus 1 times a tangent theta d theta. All right, entire denominator is gone. And so the integral of this would be, the square root of this would be 2. I'm going to go ahead and move that just to the outside of the integral. Oops, this is supposed to be squared. Secant squared minus 1 is equal to a tangent squared. And so the square root of that is just a tangent of theta times this tangent. I get tangent squared theta d theta. And that is not one of my formulas that I know. All right? But I do know from the Pythagorean identity, let me write it off to the side here, a tangent squared plus 1 equals a secant squared. So I'm just going to call this a secant squared minus 1 because I know the integral of a secant squared. So this becomes 2 times the integral of a secant squared theta minus 1 d theta. And so now what I have is 2 times integral of a secant squared is a tangent theta Integral of 1 with respect to theta is theta. So 2 tangent theta minus 2 theta plus c. But then I got to remember that I didn't start with thetas, I started with x's, so I got to convert this back to an answer that's in terms of x. So I'm going to take this thing right here and say that a secant theta is equal to x over 2, which really means a cosine theta is equal to 2 over x, just the reciprocal. So when I make my triangle here, remember, your reference angle, theta, always has to touch the x-axis. Always. You don't ever want it to be up here. So cosine theta is 2 over x. We know cosine is adjacent over hypotenuse. So there's that. This side over here should be hypotenuse squared minus the leg squared, and then square root. So x squared minus 4. I'm glancing back over here, making sure it matches, that square root. And so now what's a tangent equal to? Tangent is opposite over adjacent. So I've got 2 root x squared minus 4 over 2. This 2 came from the 2 that's right here. Minus 2 times theta. So whenever you have a theta in here, usually you want to go back to this piece right here and say that theta is equal to, if you move the secant to the other side, you have to do the arcsecant. So arcsecant of x over 2. Now, I could go back and look at this and say, well, the tangent is this over this, so let's do arctangent of this over this. Or I could say cosine is adjacent over hypotenuse, so I could do arccosine of this right here. There's a lot of different things. Usually I think what our book does is they go back to the original substitution, solve for that trig function, and do the inverse trig function of whatever's written here. Okay? So we've got arcsecant of x over 2 plus c. There's our answer. It says plus c right there. Yeah, so these trig substitution is a little bit of work. It's not quick. We got to first of all know what we're going to substitute. Got to do a derivative implicitly, substitute a bunch of trig stuff in, simplify that trig expression, then do the integral with some formula that we know, and then use this to convert everything back to x's. So there's a fair amount of work involved in these. Let's try another one. All right, so we want to solve this using trig substitution. Even if there's another way, which I'm not sure if there is, we still have to use trig substitution. You guys give it a shot. So this is interesting. I don't even see a square root. So why are they asking me to do trig substitution? But they are. So I'm going to go with it. I would look at this and say this is a squared plus u squared. So I want to let u, which is going to be x, equal a tangent theta, which a would be 1, so tangent theta. So if I take the derivative, I've got dx equals a secant squared of theta times the derivative of the angle, which is 1, and I just took the derivative of theta. All right, so now I've got to substitute all my stuff in here. So I now have the integral of, I'm going to square this, so I've got a tangent squared of theta over 1 plus tangent squared theta. And I still have to square that. And dx is equal to a secant squared of theta d theta. So, our Pythagorean identity, 1 plus a tangent squared, I know this is equal to a secant squared. So square that, you get secant to the 4th. So I've got the integral of a tangent squared theta times a secant squared theta over secant to the 4th of theta d theta. And so I would cancel those two with two of these. And so now what I have is tangent squared over secant squared theta d theta. I'd kind of like to get everything in terms of just one trig function. Now I could go to sines and cosines, see what I get there. I could do that, nothing wrong with it. But I think what I'm going to do is I'm going to go to that Pythagorean identity that tangent squared plus 1 equals secant squared. And so I'm going to convert this right here to a secant squared minus 1. So this integral becomes a secant squared of theta minus 1 over secant squared theta d theta. If I divide this into two separate fractions, what I get is an integral of 1 minus 1 over secant squared is a cosine squared. D theta. And so now by Pythagorean identity, I know that this is equal to a sine squared. D theta. And I don't have a formula for that, so I'm going to have to think of some other way to integrate this. And so I guess my thought is integration by parts. So let's see, if I take this and go back up here, I would say I don't know, this is just a guess. Let's see if this works. U equals a sine of theta, and dv equals a sine theta d theta. So I take the derivative of this and I get a cosine of theta times the derivative of the angle, which is 1, and I just took the derivative of theta. If I integrate both sides here, I get v equals integral of a sine theta would be a negative cosine theta. And so now this integral would be u times v, which would be a negative sine theta cosine theta, minus the integral of v du, which would be plus a cosine squared theta d theta, which means I'm kind of caught in the same thing here again, but if I change this to a 1 minus a sine squared of theta, so I got a negative sine theta cosine theta plus the integral of 1 minus sine squared theta d theta. Then I've got negative sine theta cosine theta. Integral of 1 would be just theta. And then minus the integral of a sine squared theta d theta. So, I don't know if you guys remember this. This happened once when we were doing integration by parts. I had the integral of a sine squared theta d theta, and that was equal to something. Get that negative sign back in there. And then I ended up with the exact same integral again. So if I brought that over here and added it to this, I would get 2 times the integral of sine squared theta d theta. is equal to a negative sine theta cosine theta plus theta. And so I just have to divide by 2, and I've got my answer. That's what I want to know what this is equal to, and I'm now saying that that is equal to, this over here. So the integral of a sine squared theta d theta is equal to a negative 1/2 sine theta cosine theta plus theta over 2 plus c. Whew. So I was just guessing at something, and it turned out that it worked. So now I got to convert this back to x's still, right? So this problem is quite a bit. So let's see. Tangent theta equals x over 1. So let me just make my triangle right here. Here's theta. Tangent is opposite over adjacent, so x over 1. Therefore, this right here is going to be the square root of this squared plus this squared. So I have the same thing here, just I've got a square root now. I didn't have that originally. So now, my answer is a negative 1/2 sine theta is opposite over hypotenuse. So x over the square root of x squared plus 1. Cosine theta is adjacent over hypotenuse. Square root x squared plus 1. Plus 1/2 arctangent of x. Plus c. So just to clean this up here at the end, I've got a negative x over square root times itself just equals what's inside, x squared plus 1, times 2. So I'm going to call that 2x squared plus 2, plus 1/2 arc tangent of x plus c. And I'm really curious to see what the calculator gets for this one. Let's go ahead and punch that in and see what happens. So I've got the integral of x squared divided by, in parentheses, 1 plus x squared, close parenthesis and square that, comma with respect to x, tan to the negative 1 of x over 2, minus x over, and they factored this, so yeah, we did that right. Wow, that's crazy. This calculator knows how to do trig substitution with an integration by parts embedded in the middle of it. That is sick. All right, that's what we have for today. Trig substitution, so let me get you guys an assignment. All right, so here's our assignment. I believe we're on assignment C15. It's on page 549. We'll do 5 to 15 odd. And just kind of a heads up, I'm working on a schedule, and I believe for this class I now have it set, let's see, June 9th is the day that we will be looking at for our Central Washington final. Don't forget, the 22nd, which is this week, is the last day that you can drop with Central. If you haven't done that yet, and that's your plan, you need to make sure and get that taken care of, okay? I'll be sending out an email with that. I'll also write up the final schedule, what we have left to cover, and just so we kind of know where we're going. And yeah, there it is. Memorial Day weekend's coming up this weekend. It's for some reason I thought that was still a week or two away. So anyway, time's, I guess, flying. Really? All right, there it is, you guys. See you tomorrow. Oh, one more thing. Since next weekend is Memorial Day weekend and Monday is a day off, that's usually my day to make videos, and I won't be in town, so that means that Tuesday's lesson won't happen. I won't be here to make that video. So anyway, just giving you a heads up, the weekend after Memorial Weekend, we will only have videos on Wednesday and Thursday. All right, there it is. Talk to you guys later. Stay safe.